Hello everyone, welcome to my talk. My name is Dengzhu Xu. I'm going to present our measurement study on commercial 5G networks. This is a joint work with my colleagues Guixin, Xi, Congkai, Yiming at Beijing University of Posts and Telecommunications, advised by Prof. Anfu Zhou, Liangliu, Huadongma, and also Prof. Xinyu Zhang from UCSD. 5G, as a monumental shift in cellular communication technology, holds tremendous potential for spurring innovation across many vertical industries, with its promised multi-Gbps speed for bandwidth-hungry applications, sub-10 milliseconds low latency for auto driving or telesurgery, and massive connectivity for IoT. Despite the huge potential, one should be cautious that it takes time for 5G to evolve and mature. The early 5G standard 3GPP Release 15, which accommodates our study period, focuses on enhancing network capacity, while low latency and machine-type communication tasks are still in progress. Also, the most recent version of Real 16 is frozen only in July 2020. It will take some time before Real 60 and 70 officially put into commercial deployment. Moreover, the current 5G deployment commonly follows the pragmatic, non-standalone mode, reusing the legacy 4G infrastructure to reduce cost. Specifically, the 5G radio only operates with the data plan and relies on the legacy LTE for control plane operationals, with sharing the same EPC. On the other hand, wireless 5G optimization mainly relies on the radio access network. The end-to-end performance of mobile applications also depends on the WLAN path, cloud service, and even the processing capacity of the end-user devices. All in all, at this early stage, one natural question is, how far away is 5G from its prospects and ecosystem? In this presentation, we demystify operational 5G networks through a first-of-its-kind measurement study. We have collected massive trees and released them on GitHub. Our measurement focuses on four major perspectives. I will first talk about the 5G coverage issue. Briefly speaking, the early 5G deployment has poor coverage even at high base station density, and there exists a large gap between indoor-outdoor coverage. We first perform a blanket measurement within our campus region with 6 500 GMBs and 13 4G EMBs. As we know, the 5G base station density on our campus is on a similar scale as the average density across our city's urban region. Therefore, we believe the campus coverage profile is representative. We traverse all road segments within our campus region, while carrying a laptop tied a smartphone to monitor the physical layer information, using a commercial toy called SIGCOMM. We then randomly sample 4,630 locations and summarize the number of locations in each RSRP, that is, signal strength coverage in the table. Despite the high deployment density, many coverage holes still exist. This is the areas with the lowest level of RSRP, unable to initiate communication services. We then only focus on the same 4G EMBs co-sitting with 5G counterparts. We found that, even under the same deployment density, the fraction of 4G coverage holes is only 3.84%, still much lower than 5G. This may be due to the higher carrier frequencies used by 5G and hence higher attenuation loss over the same distance. We now characterize the coverage profile around one typical 5G GMB. We force the 5G phone to lock on a specific cell by turning on the frequency loss switch in a diagnostic mode. The contour plot connects the symbol locations with the same base rate. We observe that the contour lines obviously deviate from the ideal sector shape, mostly biased by building blocks and multipath reflections. In addition, near the location A, B, C, and D, 100 meters from the cell 72, We use SIGCOMM to measure the bitrate in the immediately adjacent indoor and outdoor spots. The resulting plot shows that, on average, 5G has more than 2 times indoor-outdoor bitrate gap than 4G. We ascribe the large bitrate drop to the higher frequency 5G signals, which suffer more from penetration loss than the 4G signals. Considering the meager coverage of 5G indoor, we believe combining microcells in office buildings with the current microcells, such as 5G, Wi-Fi, coexistence will likely fill the coverage holes. Next, 5G claims to support Gbps bitrate and sub-10 milliseconds latency through its new radio technology and the more flat core network architecture. However, its practical performance faces many attribution factors, so we measure the end-to-end performance of mainstream transport protocols. In particular, we conduct some TCP and UDP experiments and use iPerf3 and traceroute toys, of which the server side is deployed in the code server, and the client side executes on our 5G devices. For each experiment, we log the traffic trees by Wireshark for offline analysis. Overall, our measurement is across by nature, spanning physical layer all the way up to the transport layer. We see that the UDP baseline for 5G downlink is 880 on average. We further examine the performance of 3 representative categories of TCP algorithms. We observe that for 4G, loss-based TCP and BBR performs reasonably well. For 5G, BBR achieves reasonably high bandwidth utilization. However, the traditional TCP algorithms suffer from extremely low bandwidth utilization. The result is a bit counterintuitive. To identify the root cause, we examine the packet loss under different traffic loads by sending UDP traffic at a certain fraction of baseline baseband. The results show that the packet loss of 5G sessions already exceeds 3%, even at a mild half the baseline UDP baseband. We then proper to locate the network bottleneck where the packet loss anomaly takes place. A potential reason lies in buffer overflow along intermediate routers within the end-to-end path. We thus estimate the network buffer size following the classic Stanford model. We observe that within the RAN, the 5G buffer size is 5 times over 4G, but within the wired network, the difference is about 2.5 times. As the wired network buffer takes the domain role, the buffer size on the whole 5G path is roughly 2.6 times compared with 4G. In contrast, recall that the capacity of 5G downlink is 5 times over 4G. That is, the capacity growth is incommensurate with the buffer size expansion in the wired network, which is the root reason for the high packet loss. In a word, to alleviate the abnormal TCP behaviors, we identify and verify 2 possible solutions: proper buffer sizing and adopting intelligent transport protocols like BBR. To investigate the 5G end-to-end latency, we select one example network path, a crowding of 8 hops, and measure the RTTs as hops count increases. We observe that 5G network passes achieve a network latency of 21.8 milliseconds on average. In contrast, the 3GPP standard mandates for the interactive real-time applications like tailored medicine, the transmission delay should be limited to 10 milliseconds. Clearly, the current end-to-end latency of 5G NSE is insufficient to meet such requirements. We also found that the delay reduction mainly comes from the second hop. The reduction attributes the flattened architecture of 5G. To put the above delay reduction into a big picture, we measurement the RTT of 20 remote open web services from 4 test sites and rearrange the RTTs according to the geographical distance of each path. We see that the RTTs of both 4G and 5G increase with path length, but the ratio between the gap becomes smaller as path distance increases. The findings convey a key message. The unchained latency in the wireline path, which is beyond mobile carrier's control, may neutralize 5G's latency advantage. Besides the basic network performance, the application quality of experience also depends on other factors. Here, we investigate the interplay between the communication and computing factors of immersive applications. We have deployed a Ultra HD panoramic live video Android app 360 tail, which connects to an external panoramic camera with an 8.264 hardware codec. It can stream the captured videos to the cloud server, running EZDSS RTMP service with up to 5.7K resolution and 30 FPS. We measure the video throughput at the receiver using Wireshark. We also record the frame delay using a stopwatch timing method. Specially, we use the instant camera to shoot the stopwatch T1 and then record the time from the same stopwatch displayed on the video receiver. Delta T is the end-to-end video frame delay. Figure 1 shows the results, where dynamic represents the case of constantly changing the camera views. We observe that the average received throughput of all resolution videos doesn't exceed the 5G uplink capacity. However, we also observe dynamic traffic fluctuation in dynamic sense, which occasionally overshoots the bandwidth and thus causes frame freezing. In this example experiment, we found 6 frame freezing events with a short period of 30 seconds. We can conclude that, despite enough bandwidth of 5G network capacity, the high traffic volume and the large fluctuation of video streams may cause low quality. We then measure the frame delay. Surprisingly, even for 5G, the video frame delay remains 950 milliseconds, which falls short of the requirements of real-time video telephone. We thus break down the frame delay by separately examining frame processing operational, camera capture, frame path splice, codec and video rendering, RTMP streaming and receiving, and network transmission. We found the frame transmission delay is around 66 milliseconds. We then estimated the frame capture path splice to be about 440 milliseconds. We also found that the encoding times of H.264 hardware codec is about 160 milliseconds, and the decoding time is 50 milliseconds. Overall, the frame processing latency is about 650 milliseconds in our measurements, which is 10 times over the network transmission delay for each frame. In other words, the frame processing latency conspicuous parallels end-to-end delay, even under 5G NSA pattern. Thus, it's imperative to improve the smartphone's processing capacities in order to support 5G's niche applications, which demands both high bandwidth and lowly end-to-end latency. As we know, 5G's high bitrate comes at the cost of more sophisticated signal or packet processors and radio frequency hardware. In the next section, we explore its corresponding impacts on the mobile device's power consumption. To obtain the energy consumption statistics on closed smartphones, we custom built a power logging and analysis toy called Power Stripe. Specifically, the Android kernel driver naturally supports the battery state supply and record it to the system directory. So, we can monitor the driver status periodically and put the log files in offline analysis. We first profile a 5G smartphone's energy consumption when running mainstream applications and then break down the overall energy cost into 4 parts. For instance, to get the Android system self-communication, we turn off the screen and turn on the airplane mode to kill all background applications. The results show that the 5G module dominates the energy cost, far exceeding the screen display, which is known to be the most power-hungry component before 5G. The high energy consumption of 5G radio attributions to its more powerful baseband, RF HART, and mature system-on-chip design. We also found that the total power consumption increases with application traffic intensity, such as small flows of browser and saturated traffic of file download. This implies that 5G can be much more energy efficient than 4G, but only its upper layer protocols can fully utilize its available batteries. Besides the hardware, the software energy state machine of 5G radio also plays an important role. In general, 5G radio adopts the discontinuous reception machines and opportunistically switch from RRC status for power saving. We employ the fine-graded energy traces, for example, application session, where we trigger a web loading per 3 seconds for 10 times. Comparing the same experiments for 4G, we have the following observations. The power consumption pattern of 5G shows a very obvious jagged fluctuation, which is caused by discontinuous page loading operations. Besides, 5G has an excessively long tail stage when rolling back from RRC connected to RRC idle state due to the NSA architecture, which leads to an additional waste of energy. This implies that the operator's traditional power management scheme is no longer effective for the new 5G smartphones. The above experiments indicate a simple way to improve the power efficiency of the 5G state machine. We can adopt a dynamic module selection schedule, which turns on the energy-hungry 5G module only when necessary. We design a trace route-driven simulator to verify the effectiveness of this scheme. For comparison, we employ an oracle approach, that is, with perfect sleep and awake transmission under 5G. We observe that dynamic model switching saves a remarkable amount of energy over the NR-NSA configuration for uncertain web browsing flows. The NR oracle does not show a significant advantage over NR-NSA, implying optimizing the 5G power management protocol alone provides marginal benefits, as the bottleneck may lie in the hardware itself. To sum up, we perform an end-to-end measurement study. Our measurement reveals imperative issues that hamper the performance of 5G. Some of these problems, for example, surprisingly low bandwidth utilization, can be solved through proper network resources provisioning or more intelligent protocol adaptation, but others entail long-term co-evolution of 5G with its latency internet infrastructure and ratio or computing hardware. Our measurement insights point to feasible directions to optimize 5G. For more details, please refer to our paper and open source data. Thank you.